Starting with illustration number 9, that is stated as two long solenoids are of equal length L and the smaller solenoid is connected with the larger solenoid in such a way that their axes are coinciding. Now we have to find out their mutual inductance. So here I am supposing that when the current I1 is passing through the smaller solenoid, so I1 is equals to also when this is the current is passing through the solenoid, then I can find out the strength of the magnetic field in the smaller solenoid. So B is equals to mu 0, and I am also considered that there are n1 number of turns in the first solenoid and the current passing through it is I1 and the length of long and smaller solenoids are equal, that means L. So the flux which is linked with this particular type of solenoid, or we can say the larger solenoid, is given by so this larger solenoid will also contain the smaller solenoid because of their axes are coincided. Therefore, phi 2 is equal to mu 0 n1 n2 I1 into A divided by L. See, this A shows the area of larger solenoid, and if we consider that I2 is the current flowing in the larger solenoid, then according to this relation, I have the value of strength of the magnetic field B is equals to mu 0 N2 I2 divided by L, and the flux due to this field linked with the inner solenoid is given by phi 1 is equals to mu 0 n1 n2 I2a over L. And now I have the value of phi 1. Similarly, I have the value of I2 because it is a steady current, and so now I can find out the mutual inductance. Therefore, M12 is equals to phi 1 upon I2, that is equals to mu 0 n1 n2 I2a divided by L into I2. So this I2 gets cancelled, and the final answer is mu 0 n1 n2 into A divided by L. So this is the final answer of mutual inductance. And you can also verify that M12 is equals to M21 by taking phi 2 upon I1. So with this our illustration number 9 is over. Illustration number 10. A small square loop of wire side L is placed inside a large square loop of wire which is having side L, in which the length of the large square is very greater than to the smaller loop. And here the loops are coplanar and their centers are coincide, and we have to find out the mutual inductance of the system. So first of all I am giving you the actual arrangement. So here is the arrangement is shown, in which the inner square loop is of side small l and the larger square loop is of side capital L. Now I am assuming over here that a current I is passing through the square loop of A. So here the current passing through is capital I. Also, the magnetic field at the center means this is the center, which is origin O of the loop is given by B is equals to 4 times magnetic field due to each side, because all are having the same side capital L. And now if we assume for only single side, then I can separate one particular side as L by 2, L by 2, and hence this triangle will be having the actual angle of 45 degree, because this is an equilateral triangle, and hence I can put directly the values of the angle. And according to the equation of magnetic field on a single side, therefore B is equals to 4 times mu 0 I divided by 4 pi. Here now the sides will be L by 2 and the angles will be sin alpha plus sin beta. Therefore sin 45 degree plus sin 45 degree. So here 2 to the 4, also here 2 to the 4, and if we solve this further, then this is 2 times mu 0 I upon pi L, and this is 2 times sin 45. And we know the value of sin 45 is equals to 1 upon root 2, and root 2 is cancelled with this above 2. So the final answer will be 2 root 2 mu 0 I divided by pi into L. So this is the magnetic field of the larger loop, or we can say at the center of the loop. Now here L, small l, is very less than compared to capital L, and hence the value of magnetic field can be uniformly distributed over the area. Here, the area of rectangle we have to find, or square we have to find. So it is pi L square, because all are having the same length. So this is for inner loop, and therefore the magnetic flux related to the inner loop is equals to B dot A, that is also equal to B into L square. So the value of B is with us. So I am directly writing 2 root 2 mu 0 I divided by L into, here there was a capital L, and with the introduction there was a pi. So pi into L into pi into L square. So this pi gets cancelled out. So here 2 under root 2 mu 0 I L square, and this whole term is divided by capital L. So this is the magnetic flux of the inner loop. Now, as we know that the mutual inductance for a larger system and for a smaller system, if both are having the same length, then the value of magnetic induction is same. So therefore, I am finding over here the mutual inductance of the system of two loops. That is equals to M, and is equals to phi over I, that is equals to 2 under root 2 mu 0 I L square divided by capital I into capital L. Now you see this I gets cancelled out, and therefore the mutual inductance of the system will be 2 under root 2 mu 0 L square divided by capital L, and hence this is the required equation in the illustration number 10. Let's start the illustration number 11, which is current I is passing through the central wire as well as the outer cylindrical layer of a coaxial cable in mutually opposite direction as shown in this figure. So we have to find out the self-inductance of this cable. So first of all, what I am doing is analyzing the figure. Here the current I is passing. So suppose this is the current I is passing through the central wire, and also at the outer wire. So in this wire the same amount of current is passing. So with this I can find out the magnetic field of this element, or we can say the area of cross section dx. So this dx element is from distance x at the origin. Now I can find out their magnetic field at a distance x from the central wire is given by Vx is equals to mu 0 I divided by 2 pi x. So this is the equation number 1. Now from this I can find out the magnetic flux only of this area. See, for only element Dx I am going to find out the magnetic flux. So is given by d phi is equals to dx or into L into dx. So here I have the value of dx, that is mu 0 I upon 2 pi x into L into dx, and now this is the equation number 2. So the flux passing through this space of length L and the breadth. So what will be the breadth? You see, this is the total distance B and this is the A. So this much area means B minus A will be the breadth of the two wires, and hence the flux passing through the space of length L and the breadth B minus A between the two wires. So this particular phenomenon is given by phi is equals to integration A to B d phi, because this is the area in which we have to find out the self-inductance of the cable. So that is equals to integration A to B mu 0 I L upon 2 pi x dx. Now with respect to this distance, mu 0 I and 2 pi are constant, so I am taking these quantities at outside the integration. So phi is equals to mu 0 I L divided by 2 pi integration A to B 1 over x dx. Now the integration of 1 upon x is ln x. Therefore phi is equals to mu 0 I L upon 2 pi. The integration is having the value ln x from A to B, and therefore phi is equals to mu 0 I L over 2 pi. Instead of x I am putting the initial and final value. So this is ln B minus ln of A. Now according to the law of natural logs, I can divide these two quantities B and A. So that is ln of B by A. So this is the magnetic flux. Now, according to the definition of self-inductance, is given by L is equals to phi over I. Now we have the value of phi. Substitute mu 0 I L divided by 2 pi, and this I will also come into the multiplication into ln B over A. So this I and I are cancelled out. So the answer of self-inductance L is equals to mu 0 L over 2 pi into ln of B by A. So this is the required equation. Now let's switch on to the last illustration.